Hello everyone, welcome to session 4 of the first part of linear algebra. During the previous 3 parts we saw some basic concepts about vectors and vector space, and also we talk about the rank of matrix, and we also revised some concepts of determinant of a matrix, and also matrix multiplication, system of linear system of linear equations, and so on. Today we continue, and mainly we will talk about the eigen vector and eigenvalue. The concept of eigenvectors and eigenvalue was given in session 3, in the last part of the previous session, where we introduced the concept of eigenvector and eigenvalue, and we said that the eigenvector is the direction of the base of or the basis of the matrix A. So for any matrix A, then we can find it is eigen vectors as the basis of that matrix, because it will not change the direction. So the multiplication of matrix A by the eigen vector x, as it is now in the slide, it will be like scalar, which is lambda. This scalar is called the eigenvalue, multiplied by the same x. And we said that in the first session, when we describe vectors as a quantity which has direction and magnitude. And we said also that, as you can go back to session 3, that the magnitude of the eigen vector is not important here, because you can actually simply multiply both equations by any scalar, so the magnitude can be changed easily, and then you can normalize actually this xi, you can normalize it without any change. So actually the eigen vector is non-unique, and this what let us start with this. Okay, let us start with this fact. So let us go to next page. Yeah, so maybe use smaller like size of the pen, and maybe the black one. Yes. Now, if what I mean that the value or the length is not important, if this x is eigen vector, the eigenvector, assume that it is given like 1 and maybe 4 and 0, for example. So in this eigenvector, it means that the first element here is 1/4 of the second element, and the third element is 0, and it is the same. So if we said that xi equal to 2, 8, 0, it is the same as an eigenvector. It is the same. So in general, xi equal to alpha times 1, 4, 0, where alpha is a real number, does not equal to 0, then any value for any alpha will be the same eigenvalue, eigenvector. So this is always eigenvector. So eigenvector will not change by changing the elements, but you have to have the same relation. So this is 1, this is the second one here is 4 times the first one, and the third element is 0. So it doesn't matter that you can have any alpha. For example, if you want to have the norm or the magnitude of xi equal to 1, which means that you know that the norm of xi now, or the length of xi in this case, equal to square root of 1 plus 4 square is 16 plus 0, so it is square root of 17. Okay, so if you select alpha equal to 1 divided by the square root of 17, so you can say that xi equal to 1 of the divided by square root of 17 times 1 for 0, so that now the norm of, or the length of xi equal to 1, if you like to have like unit length basis. So this is important to remember. Okay, now before we see how to solve this this equation, I like to discuss some basics here in terms of a numerical example. If we want to solve like system of linear equations, as we saw before, we know that if the number of equations is the same as the number of unknowns, and there is no linearly dependent equations, then we can solve them and we can have that single solution for that. Okay, for example, if we have, let's say, x1 plus x2 equal to 0, okay, and x1 minus x2 equal to 0, okay, this equation could be, we can put it in this form, so it is 1 1, okay, and 1 minus 1 and x1 x2 and equal to 0 and 0. Okay, are those two equations like independent or dependent? Of course, it is clear that they are independent, and you can also check that 1 times minus 1 is minus 1, minus 1 minus 1 is equal to minus 2. So the determinant of the matrix A, does not equal to 0, which means that this equation is invertible. Okay, and now to solve this equation, actually this equation has only one solution. This equation has only one solution, that x1 equal to x2 equal to 0. There is no other solution than this one. If you look to this equation, if you have system of linear equation and they are linearly independent, okay, and the number of equations is the same as the number of unknowns, like this case, and those equations equal to 0, then it has only a single solution, that all parameters equal to 0, and this is actually called a trivial solution. This is called trivial solution because usually we are not very much interested in such solution that every unknown is equal to 0, but unfortunately we don't have other option than this. Okay, okay, now let me go one step further. So assume that we have x1 plus x2 equal to 0, okay, and I have here x1 minus, it is the same, but I will put here alpha, x2 equal to 0, okay, so I added factor alpha. Alpha is any real number. So alpha is a real number, okay? It can be any real number, okay? Now, if I asked you a question, what is the value of alpha? What is the value of alpha which makes these equations that has a non-trivial solution? I repeat. Now, if we go here, we saw that in case if alpha equal to 1, then actually I will have this the same as the previous one, and the previous one, if you try it, you will never find other solution that x1 equal to x2 equal to 0, and you can actually check it here. For example, from the second equation, you can say that x1 equal to x2, and if you divide it, if you substitute it here, so it will be like 2x1 equal to 0 and x1 equal to 0 and then x2 equal to 0. This is the only solution that you can have from this equation. However, as I said, usually this is a trivial solution, and usually we are not interested in this solution that every x equal to 0. Okay, for example, if x represent like investment money, or it can represent a transmitted power or demanding power, or in mobile communication, it can be also represent the transmitted data rate or whatever. I mean, once you have system of linear equations and the solution 0, it means that you switch off your system, and this is not interested solutions. This is the reason that we call it like a trivial solution. Okay, but now by adding this alpha, What is alpha value that you can add, which makes this one to have other solution than just the trivial solution? Okay, simply, actually, if you look to this one, if we put alpha equal to -1, what happened? If we put alpha equal to -1, then actually we will have the same as the equation 1. If this is equation 1 and this is equation 2, if you put alpha equal to -1, then simply you will have x1 plus x2 equal to 0. And here I have x1 plus x2 equal to 0. And what happened now? I will have this a is equal to 1, 1, 1, 1, then x1, x2 equal to 0, 0. Actually, the second equation is identical as the first equation, or it can be just linearly dependent of the first equation, then which means that we can replace, or we can ignore the second equation and we can rely only on the first equation. And in that case, I will have some interesting solution here, is that x1 plus x2 equal to 0, and this means that x1 equal to minus x2. And here, actually, I am not anymore enforced to use only the trivial solution that x1 equal to x2 equal to 0. It is not needed anymore, because we can put just x1 equal to minus x2. So here you have infinity number of possible solutions. So if x2 equal to 2, then x1 equal to minus 2. If x2 equal to 5, then x1 equal to minus 5, and so on. So now we have this x1 equal to minus x2, even it can be infinite number of solutions, but still now we have non-trivial solution for our problem. So for any x1 equal to minus x2, we can achieve this solution. Okay, this is just a mathematical problem that we try to give some insight about it. And now let us go to the original problem of finding the eigenvalue and eigenvector. Okay, remember now this matrix becomes like singular, and the singular matrix means that the determinant of matrix A now in this case is equal to 0. Okay, remember this point because we will come back to it quite soon. Okay, let us go to the next slide. Yeah, let me go back to the equation that I tried in the previous session to explain why it comes in that way. That for any matrix A, n by n multiplied by like any vector x that equal to, and let us call it xi, so it is the eigenvector number I equal to lambda I is eigenvalue I times xi. We explain now what is the meaning of xi, what is the physical meaning actually of xi, and also what is the physical meaning of lambda I. Okay, now we are interested to find the values of the eigenvector and the eigenvalues. Okay, we are looking for the eigenvectors and eigenvalues. Remember, I just repeat again that eigenvectors is not unique vectors, and this is clear from this equation. You can multiply with any scalar alpha and it will be multiplied in both of them, so this will not this makes it like non-unique. So xi is it can be any value, but we are interested in the relation between the values as explained in the previous slide. Okay, and also remember that if you have another vector like y, and this vector is summation of two eigenvectors like x1 plus x2, assume that x1 and x2 both of them they are eigenvectors of the matrix A, then A times y is equal to A times x1 plus x2, and this equal to A x1 plus a x2, okay, and this equal to a x1. We know that it is lambda 1 x1, so it will be like lambda 1 x1 plus lambda 2 x2. Okay, so you can see that the value of ay, it can be distributed in this way. Okay, now let us go back to this equation, and let us see how could we solve this equation in order to find the eigenvalues and the eigenvectors. Okay, if we look to this equation, and if we take this part to the other side, to this side, then we will have this equation. It becomes a times xi minus lambda I xi equal to 0. Remember, this is n, a is n by n, xi is n by 1, lambda is a scalar 1 by 1, xi is n by 1, and this 0 will be n by 1. It means that it is vector with all 0 elements, okay, where we have n 0 element. Okay, and if you take xi as a common vector here, so we will have a, I am trying to bold a, but sometimes we end up with some strange shape. So a becomes minus lambda I times I, okay, multiplied by xi equal to 0. Okay, so it becomes lambda because we take that xi as a common vector. Okay, of course, just for mathematical convenience, you cannot subtract a matrix from scale. This one, it was multiplied by some vector, and we take the vector outside, then we need multiply it by I. So the reason that actually we explained this before, but I just repeat it again here for convenience. So if you have, let's say 1 0 0 1 times any x1 x2, so the result will be x1 x2, simply like that. And now this lambda I was multiplied by xi. When we take xi as like a common factor, we need to keep I, the identity matrix here, in order that when we multiply it again, then we have xi again instead of I. Okay, and now we have this equation, and we want to find what is xi and lambda I, which makes this equation equal to 0. Remember, we are interested in non-trivial solution. Okay, we are interested in non-trivial solution, because if you said the solution, which is correct actually mathematically, that xi equal to 0, this will achieve this equation. Xi equal to 0, this will achieve this equation, but it will be a trivial solution. It will be a trivial solution, and we are interested in a non-trivial solution in order to find the eigenvector. So the eigenvector should be a non-trivial vector. It cannot be all 0 vector. Okay, and in order to find this solution, remember, this is very important, this matrix, because now we have a new matrix. This new matrix is A minus lambda I times I. This matrix must be singular matrix. This matrix must be singular matrix in order to have the eigenvectors to be a non-trivial vector. To be a non-trivial vector, this matrix must be a singular matrix. It means that A minus lambda I times I, okay, this one must be singular in order to have a non-trivial singular value vector. Okay, how to make this singular? It means that the determinant of A minus lambda I times the identity matrix I must be 0. Remember, the determinant of any matrix is a scalar, so this 0 is a scalar. Okay, so the determinant of A minus lambda I times the identity matrix I must be 0 in order to have a solution for the singular values and singular vectors. Okay, now the question, so actually finding the xi and lambda I has been divided into two steps. The first step, that we should find what is lambda I, the eigenvectors or the eigenvalues, which makes this equation equal to 0. Once we found them, we can substitute here and then we can find the values of xi. Okay, now let us do that in some with some numerical example. Okay, we go to next page. By the way, during all the examples that I am giving here, numerical examples, actually all of them that I just give them during the explanation, so they are not prepared before that, for this reason that it is expected, of course, that I may make some computational error here, but however, that of course if I found it after that, I will either add a message or add the text in the video that to correct the answer, or if you can find any error, that just remind me during the online session. Okay, now I'm just want to assume any matrix A, so I will assume that, of course, we will take a small matrix and then just to explain the concept here. So let us take some matrix like 1, 2, minus 1 and 0. Okay, so it is clear actually this matrix is non-singular. Okay, you cannot make generate any of these rows and columns from the other, and then let us find the eigen value in the beginning. So the first step is to find the eigenvalue. Finding the eigenvalue, as I said, we need to have the determinant of A minus lambda I. Why we said lambda I? Because this matrix is 2 by 2, which means that generally we will have 2 eigenvalues and 2 eigenvectors. Okay, and this lambda I, so of course I can be 1 or 2, okay, times I, this should be 0. Okay, it means that the determinant of A, which is 1, 2, minus 1, 0, minus lambda times I, so I is 1, 0, 0, 1 multiplied by lambda, so it becomes like lambda I, okay, 0, 0, lambda I. Simply, it is lambda I times 1, 0, 0, 1, and this will have this form. Okay, and this makes like the determinant of 1 minus 1 minus lambda I. This one, 1 minus lambda I. 2 minus 0 is 2. Okay, minus 1 minus 0 is minus 1, and 0 minus lambda I is minus lambda I. Okay, and this should be 0. Okay, now if you remember how to find the determinant of any matrix, we explained this before. So we multiply the diagonal element together, so it is 1 minus lambda I times minus lambda I. It means that it is minus lambda I plus lambda I square. Okay, and then minus 2 times minus 1, it becomes 2 minus minus, it becomes plus 2 equal to 0. So the equation, it becomes like second order equation. It is lambda I square, okay, minus lambda I plus 2 equal to 0. Okay, now we can find lambda I actually. So lambda I equal to, it becomes like minus, it becomes a minus 1, it becomes plus 1 plus minus square root. Okay, this will be like this minus 1, it becomes square, minus 4 AC, so it becomes 1 minus 4 times 2 is minus 8, okay, divided by 2. Okay, so which means that actually this lambda for this matrix is a complex number. So we have actually lambda 1, the first eigen value, it becomes half plus the complex number j, square root of 7 divided by 2, and the second eigen value is half minus j, square root of 7 divided by 2. So now we found the eigen values, two eigenvalues with which are associated with this matrix. Fortunately, in machine learning and in deep learning in general, actually most of our matrices, as I said, they will be the covariance matrix. We deal with a covariance matrix, and covariance matrix always it has real eigen values when we have symmetric matrix, because covariance matrix is symmetric, and all symmetric matrices, when the elements are real numbers, then the eigen values will be also real numbers. But now with this example, as I said, I just invented this matrix now, so we had this complex number, but it doesn't matter, because my aim here is just to explain how to find the matrix, the eigenvalues of a matrix. Okay, now let us make another example, because okay, because it is better to have a matrix with real eigenvalues. So now I will make this A. Let us have matrix A, which is a symmetric matrix. So a symmetric matrix can be anything in the diagonal, for example 3 2, but let us here we have 1 1. Okay, so now we have a symmetric matrix, and in this matrix for sure that the eigen values will be real numbers. So the determinant again of a minus lambda I times I equal to 0, then the determinant of it becomes like 3 minus lambda, okay, 3 minus lambda I, of course, and then 1 minus 0 is 1, 1 minus 0 is 1, and 2 minus lambda I becomes 2 minus lambda I in this case. Okay, and this determinant actually it will be like 3 minus lambda I times 2 minus lambda I minus 1, so it becomes like 3 minus lambda I times 2 minus lambda I, okay, minus 1 equal to 0. Now we can expand this equation. Of course, you can do it also with any calculator or advanced calculator or any computer package, but here let us do it by hand, step by step. So this will be like 3 times 2 is 6, okay, and 3 minus 3 lambda I, okay, then minus 2 lambda I, then plus lambda I square, minus 1 equal to 0. Okay, and then you can see here that it is lambda I square minus 5 lambda I minus 5 lambda I, and then it becomes here 6 minus 1 is equal to 5, so it is plus 5 equal to 0. And now lambda I equal to, this becomes 5 plus minus square root of 5 square is 25 minus 4 times 5 is 20 divided by 2, so it will be like 5 or divided by 2, which is 2.5 plus square root of 5 square root of 5 divided by 2, or this is lambda 1, or 2.5, because it can be plus or minus 2.5 minus square root of 5 divided by 2. So you can calculate it with your calculator, and then of course as an approximation, if we approximate square root of 5 like 2.1 for example, and or 2.2, then we will have like 4.7 one lambda, and the other lambda will be like 0.3 or something like that. Okay, so we can say that this is about I don't have calculator now close to me, so it is almost like 4.7, and this could be around, if we said that sorry, square root of 5 is about 2.2, but it is divided by 2 actually, so it will be like 1.1. so 1.1 plus 2.5, it will be 3.6. so let me take the eraser here. Okay, so it will be like 3.6 about, and this one will be like 1.4 or something like that. So actually don't take this very close to the real or the actual number, just approximation. So the idea here that just to have the approximation for lambda 1 and lambda 2. Okay, now let us see how to find the eigenvectors. Now we approximate about the eigenvalues, how to find eigenvectors. Okay, let us go to another slide. Okay, now we said that A, matrix A times X, we said I equal to lambda I times Xi. Okay, as we said that lambda 1 is about 3.6, for example, in the previous matrix. Okay, so the matrix A, which okay, I think it was, now I forget it, so it was a 3 1 1 2. Okay, 3 1 1 1 2. Okay, times, so this is x1, which is the first eigen value. So let me dot like u1 and u2. This equal to 3.6 times u1 and u2. Now our question is to find what is u1 and u2. This will be for the first eigenvector. Of course, we can repeat it also with lambda 2 equal to, for example, if we said that it is 1.4, for example, then we can repeat the same. Okay, now how to find this? So we can just make the matrix multiplication with vector, so it becomes like 3 u1 plus u2. This is the first equation, as you can see it. Okay, so we can put it in this way, and the second equation is u1 plus 2 u2, and this will be like 3.6 u1 and u2. Okay, so in other words, it becomes like 3 u1 plus u2 equal to 3.6 u1. This is from the first equation, from this part, and the second equation is u1 plus 2 u2 equal to 3.6 u2. Okay, now you can say that, for example, u1 equal to 3.6 u2 minus 2 u2, which means that it will be about 1.6 u2. So u1 equal to 1.6 u2. You can substitute this here in the above equation. So now we will have only that equation in u2. So now we have actually the relation. You can see that u1 equal to 1.6 u2. If you substitute it here, actually you will have the same. You will have the same relation. What that means? It means that if we said that u1 is alpha, then this is the first eigenvector. It will be, if we said that u1 is alpha, then u2 is 1.6. Yes, u1 is, so it will be alpha divided by 1.6. So this will be the first eigenvector. This will be the first eigenvector. Now, if you substitute this one, for example, u1, 1.6 u2, 2, it will be like if you multiply this by 3 plus u2, you will have the same ratio. You will have the same ratio. Okay, why? Because now these equations are singular, so it is actually both of them, they are linearly dependent. Okay, now this will be the eigen vector. So the eigenvector is alpha and alpha divided by 1.6. You are free to select alpha. For example, you said that I want alpha equal to 1.6. It is okay. This x1 equal to 1.6 and 1. This will be the first eigenvector. Okay, if you want to put alpha equal to 2, equal to 3, you can do whatever you like. Okay, and now we can repeat the same process, but instead of putting here lambda 1, you can put here lambda 2, and then you will find the second eigenvector. It will be also like some ratio between two elements. Now you found what is eigenvector and the value of the eigenvalues and eigenvectors. Okay, so this is the way that you can compute them. Now I will finish this session by extending this result that we have found. So now A, we said that times eigenvector xi, it gives you lambda I times xi. Okay, what if we collect all eigenvectors in one matrix? So let us define x capital as a matrix with x1, x2 till xn. Remember that each x here is eigenvector. So this is the first eigenvector, the second eigenvector, and so on. Okay, which means that A times x1 equal to lambda 1 times x1, and A times x2 equal to lambda 2 times x2, and so on. Okay, now what we can do here, we can, if we put this kind of implementation, this is x capital. This x capital, which is a matrix, contains all eigenvectors together, and this will be of course n by n matrix. Then if we multiply it in A, so we will have A times x capital in this way. Okay, actually this will be the same as x multiplied by another matrix Z, and actually this Z matrix is nothing but the diagonal matrix with the eigenvalues. So this Z matrix is a matrix with lambda 1, lambda 2, of course the others are zeros. Okay, 0, 0, lambda 3 till lambda n. So it will be like n by n matrix, but the diagonal is the eigenvalues. The diagonal is the eigenvalues of the matrix A. Okay, and now if you multiply by the inverse of x in both sides, so if you multiply here by x inverse and here also by x inverse, actually you did nothing, but x times x inverse is the identity. So this one will be the identity matrix, and A times the identity matrix is actually nothing but A. So A equal to x times the diagonal matrix with the eigenvalues times x inverse. Actually this equation, and this beautiful equation actually is one of the most important equations in linear algebra. So if you allow me to write it in red color, so any square matrix A, okay, square matrix A could be decomposed to a matrix X, which is matrix with eigen vectors times diagonal matrix, and this diagonal matrix contains eigenvalues and the other elements equal to 0 times x times the inverse of this x. This is called eigen vector or eigen decomposition. This decomposition is called the eigen decomposition. So the matrix could be decomposed into these two matrices. So X matrix, X inverse matrix, and in between we have a diagonal matrix which is which contains only the eigenvalues in the diagonal. So actually this is very interesting equation, very interesting equation. It has many applications, and it is related to the decomposition of a matrix. We can look inside, assume that this A is a matrix of data. Then by this decomposition we can look inside the data, and we can retrieve like some hidden information about this data. But just like an example, what happens if you have like matrix A square for this one after decomposition? It will be like X times the diagonal Z or Z times X inverse times the same, actually, because it is square, so it is A times A. It will be also again times X times Z times X inverse. So what is here? It is X inverse times X is nothing but the identity. So here we have the identity matrix. So A square is X times Z square, because Z times Z is Z square or Z square times X inverse. Okay, so actually this could be extended in this way. So in general, if the matrix A for any power m is nothing but X times the diagonal matrix of the power m times X inverse. Okay, this makes a great simplification of taking power of matrix A. Why? Because for any diagonal element, for example, if you have here let's say 3, and here you have 4 and 0 0, this is diagonal matrix. If you want to take let's say of the power of 2, you don't need to make any matrix operation or matrix multiplication. All what you need is just to take the square of the diagonal element, because it is a diagonal matrix, and this is general. For example, if you have 1 0 0 0 2 0 0 0, let's say 3, and I want to take a cube of this matrix, then simply it will be 1 0 0, because 1 cube is 1, 0 2 times 2 times 2 is 8, 0 0 0 3 times 3 times 3 is 27. That's it. However, if you want to take the cube of any other matrix, you need to take the multiplication of matrices in the way that we showed before, 3 times. So of course for this one is easy to find, but just think about bigger matrix and of the power of 20, for example. It is very difficult to do it in by hand, at least. Okay, and actually even by many mathematical packages they do it in this way. So all what they need just to find the matrix of eigenvectors, because those you need to find them once actually, and then for any power of the matrix, just take that power to that to the diagonal element or diagonal matrix. It is not only positive power, it can be also the square root or whatever that you want. For example, if you want to take the square root of A, this could be done easily here in this way. Okay, so that's all about this like introduction of the eigenvalue and the eigen decomposition. Of course, we are coming many times in this course to this concept, and it is important to try yourself with some examples. Of course, you can if you have Octave or MATLAB, there's like built-in function is determinant function of A. It gives you the determinant. If you put eigen of A, it will give you the eigenvalues and also eigenvectors. So try to try yourself with just invent 2 by 2 matrix and try to solve it by hand to find the eigenvalue and the eigenvectors, and then try it with the computer to see if it is correct or not. Okay, thank you very much, and see you in the next session. Thanks.